Hello, welcome to today's seminar. Our speaker today is Patrick Bennett from Western Michigan University, and he will be speaking about K2 to 3 process in bipartite graphs.
Thank you. It's very nice to be here. Good, I don't need to point directly at that. So, I'm going to talk a little bit about independent sets and hypergraphs, first of all. A hypergraph is just a set of vertices and edges like a graph, except now the edges can be any size. In a graph, the edges have size 2, but in a hypergraph, they can be any size. If they all happen to have the same size, we call it the same size K specifically, we call it a K uniform hypergraph. So in particular, a graph is just a 2 uniform hypergraph. And how does the concept of an independent set generalize to hypergraphs? Well, maybe it's not so clear, but the generally accepted generalization is that the independent set just should not contain an entire edge, which does correspond to what we think of as an independent set in a graph. It just doesn't have both endpoints of an edge. So, well, here's a hypergraph, and the blue vertices are an independent set. It does not, these bubbles are the edges, and no edge has all 3 of its vertices blue. Alright, so why am I talking about this? It's because a lot of problems in combinatorics can be stated in terms of independent sets and hypergraphs that we don't always necessarily think of that way. For example, Semiretti's theorem, the theorem that says that if you have epsilon n numbers between 1 to n, then you have a k-term arithmetic progression. That can be stated as follows. Let H sub KAP be the hypergraph whose vertex set is the numbers from 1 to n, and whose edges are all k-term arithmetic progressions. So this is a k-uniform hypergraph. And it's just saying that this hypergraph does not have a linear size independent set. Okay, so this gets a little weird, but here's Mantel's theorem stated as independent sets and hypergraphs. So more familiarly, we know Mantel's theorem is just, it's about how many edges can you have in a triangle-free graph. So here's a picture of a triangle in a graph, but consider the following hypergraph that I'm going to call H sub K3. This will be a 3 uniform hypergraph, and so I'm trying to illustrate this correspondence here. If we're considering an n vertex graph, I'm going to form this hypergraph. The vertices in the hypergraph are pairs of vertices in the graph, or you could think of it as potential edges in the graph. And 3 vertices in the hypergraph form an edge if the corresponding 3 edges in the graph form a triangle. So Mantel's theorem basically says that this hypergraph has independence number that. And there are advantages to think of it this way, but also disadvantages, because it's easy to visualize this. Like, we know what triangles look like, but it's a bit harder to visualize this hypergraph, but it can be helpful to think of it this way. Also, say for diagonal Ramsey's theorem, again, we just saw H sub K3, but as you can imagine, there's such a thing as H sub KT, where a T clique in the graph corresponds to an edge in the hypergraph. So I would state diagonal Ramsey's theorem as for every T there's some n such that the vertices of this hypergraph can be partitioned into 2 independent sets. Maybe this is more natural to describe as a hypergraph coloring problem, because you're partitioning the vertices into independent sets. Okay. So now let me talk about the independent process. So you don't have to read all of those words. I'll tell you what they say. We are going to start with our hypergraph. It's the same hypergraph that I showed you. And we are going to choose one vertex at a time. We're going to start with an independent set that's just the empty set. It's clearly independent. And then one at a time, I'm going to throw one vertex into my current independent set, just with the restriction that it remains independent. So I'm not going to choose a vertex that completes an entire edge together with vertices that I've already previously chosen. Okay, so in the beginning all the vertices are black, and I'm going to start turning them blue if I've declared that this one's in my independent set. Okay, so I've chosen one, and then for my next choice, there's really no danger. I'm not at risk of completing an entire edge. So really by the way, specifically, at each step, I'm choosing a vertex uniformly at random from the ones that are eligible to be chosen. Meaning, out of all the vertices that I could add, I just pick one uniformly at random, all equally likely. But currently, they're all eligible, so I'm just picking a random black vertex and turning it blue. And, okay, now I look at it, there's still no danger, so I'll just pick a random one again. Okay, now there's danger. I'd better not pick that one next, so I'm going to turn it red. So now you see how this goes. Vertices are they go from black to either blue or red. And so now I'm going to pick a random black one. Okay, I picked that one. Now I better not pick this one, so I turn it red. And then at the last step, I pick that one. So that's the process. Let's take a different view of that process. So remember the hypergraph H sub K3, which corresponds to a graph. The edges of this hypergraph are triangles in the graph. So what I'm going to do is I'm going to show you the triangle-free process, but I'm going to show you the graph view of it because it's easier to visualize. So the things that we're choosing are not vertices. The things that we're choosing are edges. So I'm going to choose a thing and turn it blue. And then, well, for my next choice, there was no danger of creating a triangle, so I just pick a random potential edge and turn it blue. And I keep going. Okay, so now there's some potential danger, so this will turn red. And yeah, so you guys probably get it. I'll click through. And you run until every edge is either blue or red. So this is probably the most I'm very confident saying that this is the most well-studied instance of such a process, and maybe one of the earliest studied. And I won't tell you the whole history of it, but I'll tell you the cutting edge. Here's a result by Bowman, Kivosh, and independently Fizz, Ponteveros, Griffiths, and Morris, that they determined asymptotically, even including the constant, how many blue edges you end up with at termination with high probability. By the way, just in case somebody doesn't know, with high probability means probability tending to 1 as n goes to infinity. So we're thinking of running this process on a larger and larger number of vertices. And the probability goes to 1 that these events happen. Also, so they analyzed the clique number of the red graph, and they found that it's, well, at most asymptotically this, and that gives a Ramsey bound, right? Because what did this process do? We get one thing for free, which is that the blue graph doesn't have any triangles. We did a good job of that. The other part is the clique number, and that might be hard. We don't get that for free. This process isn't doing anything that would deterministically forbid large red cliques, but just probabilistically, it's unlikely to have a clique bigger than that. So that proves the existence of a graph with no blue triangle and no big red cliques. That gives you Ramsey. And this is exciting because it's matching up to a constant, like I've got a 1/4 here and just a 1 here. It's matching up to a constant, the best known upper bound on that Ramsey number. So it's just a factor of 4, which is not much at all. Okay. So here's a theorem that Wolfowitz proved about the triangle-free process. Pick your favorite graph, F, and we want to count the number of blue copies of F that show up in the triangle-free process. Now, if your favorite graph happens to have a triangle in it, then there's not going to be any copies of F. However, if your graph does not have a triangle, then something interesting happens. The number of copies is, well, maybe just looking at this number doesn't really excite you, but let me describe it this way. This is the same number of copies of F as you would get in a uniform random graph with the same density. Meaning if you just took however many blue edges you're ending up with, take that number of blue edges and make a different graph where you just choose each edge with equal probability. Like that, this is a simple uniform random graph that I'm talking about. And that simple uniform random graph has as many copies of F as this. So this is what we call a pseudorandom property, which is a bit weird to use the word pseudorandom for something that's literally random. But there's a reason for this historically. Pseudorandom means resembling something that is like simple and random, like the uniform random hypergraph where each edge is chosen with equal probability, like a uniform random thing, not this complicated process. But calling it pseudo-random is just saying that this more complicated process in some ways resembles a uniform random one.
So I have a quick question. Is there no normalizing constant for, so we're not doing this isomorphic copy?
Oh, labeled copies.
Labeled, sorry.
Yeah, I didn't want to write 1 over automorphism factorial, that stuff. Yeah, good point. Okay, so this generalizes to, say, the Gfree process, where instead of avoiding a triangle, you're avoiding whatever graph G is. Bowman and Kivosh analyzed that process for a broad class of graphs G. They found a lower bound on the final number of blue edges, and I should mention that on the previous slide, I said that for when G is a triangle, they nailed it. They got asymptotically even the constant, so matching upper and lower bound. That's generally rare for these processes. Lower bounds are easier than upper bounds. But they got a lower bound, and this is a generalization of what it is for triangles. It's suspected that the matching upper bound should hold, at least up to a constant, but hard to prove and rare for these instances. So as a result of their work, it improves lower bounds on a Turan number, which is, it's easy to imagine. You're trying to avoid the graph G, so you end up with a graph that doesn't have any copies of G. And for some graphs G, the number of edges that you end up with, it actually beats the best known thing for start over. It beats the best known construction anyone has come up with for any Gfree graph maximizing the number of edges.
Patrick?
Yeah.
Has anybody even tried to do a G1 and G2 free process?
People have strongly suggested that it should be considered, but to my knowledge, it has not been done. People have, so specifically I know people have, I forget who, but they suggested that you forbid all cycles up to a certain length. It's like they call it the girth process. So they also analyzed subgraph counts in the blue graph, which is sort of a generalization of this Wolfowitz result that I told you about, and the clique number of that red graph. And the answers to both of these were pseudo-random. Like, how many copies of your favorite subgraph are there? Well, if your favorite subgraph happens to have G in it, then there's going to be 0. But if it doesn't have G in it, then it's going to be pseudo-random. And what's the clique number of your graph? it's the same as the clique number of a uniform random graph with the same density. And because they analyze the clique number, this again gives some lower bounds on Ramsey numbers. Okay, so now this is starting to touch on work that I had something to do with. So with Bowman, we proved the following theorem, which is about any independent process on any hypergraph. Well, not any hypergraph, it has to satisfy some technical conditions. But this is, in a sense, it's a generalization of parts of Bowman and Kivash's Gfree paper. For example, if you just consider the hypergraph that corresponds to the Gfree process, where each potential edge is a vertex in the hypergraph, and each potential copy of G is an edge in the hypergraph, and just apply our theorem, and the hypergraph does satisfy these technical conditions, so you just apply our theorem and you get the same lower bound they got. This also, now you can consider, say, the Gfree process where G is a hypergraph. So you have all these, dangerous for me to do this. That doesn't work. Oh, maybe chalk is better. So, I won't make this too complicated. Is there red chalk? Okay, we'll pretend that orange is red. You start choosing hyperedges. I assure you this is random. But you're forbidding a specific sub-hypergraph. So I'm not being too specific. But if you see that you're in danger of forming the forbidden sub-hypergraph, certain edges may turn red, which is orange. So it applies to that, which in turn can give us some actual best-known lower bounds on hypergraph Turan numbers, because you managed to come up with a hypergraph without any copies of whatever your forbidden hypergraph is. And for some hypergraphs, that's the best known bound. So it also applies to other interesting hypergraphs, including the hypergraph that I told you about, K-term arithmetic progressions, where the edges are K-term arithmetic progressions. And so the following is, for most hypergraphs, this isn't the actual independence number. Most hypergraphs have independent sets that are significantly bigger than this. And that includes a lot of the hypergraphs that we would be interested in. However, it's worth mentioning that there do exist hypergraphs for which this actually is essentially the independence number up to a constant, whatever constant is being suppressed by this omega. So it doesn't always do a terrible job of finding a large independent set. But usually what we're interested in isn't the sheer size of the independent set that we produce this way. Usually we're interested in a combination of the size and some pseudo-random properties. But sometimes the size is, sometimes you can actually get something good for the size. Anyway, Bowman, Mubai, and Piccolelli used this theorem for hypergraph Ramsey numbers. So it's like that, I drew a little cartoon of the Gfree process where G's a hypergraph over there. And if you analyze the clique number of the red hypergraph, then you get a Ramsey bound. So that's something that they did. So here is another theorem that we proved, Bowman and I. And this is a generalization of the Wolfowitz thing. If you remember the Wolfowitz thing, it was about counting copies of your favorite graph in the triangle-free process. So the generalization is as follows. Imagine I have my hypergraph H, and then on the same set of vertices, I have another hypergraph H prime. And that they say H is like K uniform and H prime is S uniform. It doesn't, the edges don't have to be the same size. What we're going to do is we're going to run the independent process on H, meaning I'm just picking vertices one at a time as long as I don't choose an entire edge of H. But I might have edges of H prime. In fact, for most cases, I probably do have edges of H prime. And what we do is we count how many of them are contained in our independent. In the set that is independent for H, we count how many edges of H prime there are. And it's pseudo-random. It's about as many copies as you would expect if this were a uniformly random set of vertices. So, for example, this allows us to do the following. We can run the Gfree process and count how many copies of G prime there are, but Bowman and Kivosh kind of already did that part. It also applies to a process where, say, we're choosing numbers one at a time and we're avoiding solutions to a certain equation, and then we're asking the question, so say there's two equations, E1 and E2, and we're avoiding solutions to E1, and then we're asking the question, how many solutions to E2 are there in our set? And that should be pseudo-random. And we used these theorems to analyze the Gowers norm in the process that avoids K-term arithmetic progressions. So, if anyone knows a lot about the Gowers norm, I'll probably make a fool of myself, so don't be too harsh. But from my perspective, the Gowers norm of a set is, roughly speaking, it's a measure of pseudo-randomness and density. If a set of numbers is dense enough, there's enough of them, and it's sufficiently random looking, then the Gowers norm should be small. So there was a question asked by Gowers and Green about if the Gowers norm is small, meaning that the density should be high enough and it looks random, if that's the case, must this set contain a K-term arithmetic progression? And so what we did was we ran the K-term arithmetic progression free process, and it gets up to a certain size, and it's also pseudo-random. So roughly speaking, the answer is no, to an extent, to the question that they asked. We produced a set that was sufficiently pseudo-random and did not have any K-term arithmetic progressions and was dense enough. So let me say a little bit about the proof. So I've shown you enough pictures now where maybe you understand this. Let's say we're in the middle of the independent process. We have some red vertices, some black ones, and some blue ones. So how does this evolve? What I'm really interested in is how long the process lasts, first of all. The process lasts as long as there's any black vertices left. And so let's let Q be that number of black vertices. So then let's try to understand how Q changes. Well, at each step, oh, I'm getting a little ahead of myself. Wait, maybe I'm not. Okay. At each step, I choose a black vertex and I turn it blue. But then maybe that forces more vertices to turn red. In particular, that's, okay, I have a laser, so I'm not going to point with my finger. It's going to turn these red. So the question is how many, I mean, it's easy to understand how many turn blue, which is one per step, but it may be a bit harder to understand how many turn red. So we define this other variable, d2 of v, to be, let me go back just 2 steps. If this is v, d2 of v is just the number of edges containing v, one more open vertex and one vertex in S. And by the way, we're assuming that this is a 3 uniform hypergraph right now for simplicity. So all the edges are of size 3. So these 3 edges were really the edges that caused the vertices to turn red. That's what we count for d2 of v. And we do that simply because we're interested in tracking q, and that tells us how much q changes in a step. Well, okay, so now this sort of snowballs, right? We were initially interested in q, and that sort of forced us to be interested in this other variable d2. And so now let's try to see how d2 changes, and this gets a little bit more complicated. Here's v. So how in one step can d2 of v change? Well, we can gain d2s and we can also lose d2s. Here's how we can gain one. Okay, so what just happened? So I'm about to turn that vertex blue. And that's how you gain a d2, right? This is an edge, this one, that wasn't a d2, but now it will become a d2. Also, there's 2 ways for this to become a d2. I could choose that vertex or that one. And so this is supposed to explain this term. d3 is the number of edges that look like that. But d3 is the number of edges that contain v, and every vertex is black. And those can turn into d2s if you choose one of them. Okay, so that's a thing that can happen. Sorry, I'm clicking around too much. We can also lose d2s. Yeah.
We're sticking with 3 uniforms for the moment, right?
Yes.
For this discussion.
Yes. We can also lose d2s. There's a couple of ways we can lose d2s. So here's an edge that is currently counting as a d2. So what could happen where it wouldn't count as a d2 in the next step? Well, I could choose that vertex, but more likely, it turns out, the more likely way I could lose this vertex is if I closed that vertex, meaning it's going to turn red. In other words, the most likely way for this vertex to get lost here is if I choose a vertex like that, and that'll turn that one red. So how many ways are there for that to happen? Well, for every edge that v is in that looked like that was a d2, and I'm going to do a sum over possible d2s, all of the ways to close that vertex is what I want to count, meaning I sum up d2 of its neighbors. So, right. This, as I said, it starts to get complicated, but, and there's some fear that this snowballing effect will just keep going. Like, okay, we started wanting to track Q, and then we said, well, that means we need to track D2, and now we said, well, if we're going to track D2, then we need to track D3, and then, well, you might be afraid of what we need to track for D3. It turns out that that's about it. It turns out that if you want to describe how much D3 changes in one step, you can describe it in terms of all total. How many of those edges should count for D3? Well, it's just however many of those edges have both of the other vertices open, and that should be Q squared. If we think of lowercase q as the probability a random vertex is open. And then we have concentration inequalities that say that these random variables actually do stay close to these trajectories. And if you analyze, once again, we were just trying to determine when Q gets small, and we have these error bounds, right? This is really a random process, so these variables are not guaranteed to be that close to these predictions, and the error bounds blow up at some point. So at some point, you're not able to say anything anymore, but fortunately, that's not until we get to this step, which is well, for the case k equals 3, this is the lower bound on on the size of the final independent set. So I should probably skip the next part for now about these technical conditions on the hypergraph. So, yeah, I might come back to this, but yeah, I should actually make sure to get to the title of the talk, right? So what is the bipartite Ramsey theorem, problem? So this was introduced by Beinecke and Schwenk in '75. BR of ST is the smallest n such that any red-blue coloring of KNN has either a blue KSS or a KTT. So it's essentially, you can describe this as, it's just a Ramsey problem for a different host graph. The standard Ramsey problem is when your host graph is Kn. And well, if we change the host graph to a bipartite graph, then the things that we're looking for better also be bipartite. So initially, Beinecke and Schwenk proved these numbers exist, and they proved, for example, that B22 equals 5. So I like that one. I can show it to you real quick. So this is, they say every talk should have a proof and a joke. I don't know if I really have a joke, but it's your classic majority argument here. Out of the 5 vertices on top, there must be 3 with the same majority color. Without loss of generality, assume that there's 3 of them whose majority color is blue. So there's 3 vertices on top, each of which has 3 blue neighbors on the bottom. So, well, without loss of generality, maybe the first one looks like this. And then for the second one, I'm not really in trouble because I'm trying to avoid a blue K2-2, but I'll be able to do it. I just can't share 2 neighbors. I'm forced to share 1, but that's okay, I can do this. But then when I go for my third vertex, I'm done. There's no way to draw 3 neighbors without completing a blue K2-2 here. Oh, and I guess that's the upper bound, but for the lower bound, you just color. Find a way to color K44 without any red or blue K22s, and you'll have fun for a minute and find it. So, what is known about these things? First of all, the diagonal case, where the parameters are the same. The best known lower bound is this by Hatting and Henning, and that just uses Lovász local lemma, a lot like Spencer did this for the standard Ramsey numbers. It's analogous to that. And Conlon has the best known upper bound here. I keep meaning to read that paper. It's only 4 pages long, but I don't know what his method was. What about the off-diagonal case? Meaning, if I fix S and let T grow, then we have these bounds, which are from Caro and Russo. The lower bound is again Lovász local lemma. And for the upper bound, it's just a density argument. We have these Zerenkovich numbers, which are just, it's like a bipartite analog of the Turan problem. You're trying to find the largest number of edges that you can pack into a bipartite graph and avoid some other bipartite graph. and those numbers actually turn out to be small. This is kind of a departure from Turan numbers. Turan numbers for cliques are sort of big. You can actually have a lot of edges in a graph and avoid a clique. And you can have a dense graph that avoids a clique, but it can't be that dense for the Zrenkovich problem. And so there is a density version. Like the argument just goes as follows for the Ramsey bound. You have a graph, all the edges are red or blue. Pick the majority color, either most of the edges are blue or most of them are red, and then just use the Zrenkovich bound. You just can't have that many edges in a graph that avoids a red, whatever you're trying to avoid. Okay, so what did we do? With Deepak Bal, we improved the lower bound for the case s equals 2. We improved it by a factor of square root of log. Right, because we plug in s equals 2, you get t to the 3/2 over log to the 3/2, and the bound we're now giving has t to the 3/2 over just log. So that's the improvement that we got. And this is all very parallel to the story for standard Ramsey numbers. There was a time when the best known bound for standard Ramsey numbers was given by Lovász-Lóka lemma, and then Bowman-Kivász came along and improved that, but the improvement was just a power of log. When we're talking about triangles, that improvement by a power of log actually matched the best known upper bound. But for most, they also improved lower bounds on other Ramsey numbers, but none of those match the upper bound. So it's maybe less exciting, but it's still an improvement. And as you might imagine, the proof idea is the bipartite K2 free process, meaning it's kind of what it sounds like. I'm going to run a process. The host graph is going to be bipartite. So I'm only going to add edges from the top to the bottom, and I'm going to avoid a blue K2. So here I go. Maybe I will go too slow here. Okay, so now there's some danger, so this will turn red. And then it starts to get complicated pretty quickly as you have more blue edges than each additional, so a lot happens. A lot starts happening in one step. Like, I draw this blue edge and that creates a ton of danger. Like, basically, okay, when I connect two vertices, if I connect this one to this one, then I look at the neighborhood of this one and the neighborhood of that one, and all of the edges from this neighborhood to that neighborhood turn red. And that's what just happened. Right, we get some things for free thanks to the general theorem that I proved with Bowman. You just have to, you have to talk about, of course, this, as you can imagine, corresponds to the independent process in the appropriate hypergraph, where the edges of this graph correspond to the vertices of the hypergraph, and K2's in the graph are edges in the hypergraph. And you just check that that hypergraph satisfies the technical conditions of our general theorem, and it does. It's not too hard to check. So that theorem gives us a number of things, including that the final K2 free blue graph that we're making, we have a lower bound on the number of edges in it. What that theorem does not give us, so the work we have to do is show that there's no red KTT. And so I can't really explain this too much, but to get the specific Ramsey bound that we want there to be no red KT for T on the order of about, say, this. So let T be about that, and now I'm showing you a picture of the graph. Imagine that this is T, I guess T's 4 here. And so our strategy is to show that every possible KTT has been hit with a blue edge by the time we have this many edges total, there does not exist a set of t vertices on the top and a set of t vertices on the bottom without a blue edge in it. That's what we're going to show. And that starts to get hard. You know, this is a probabilistic argument, and there are a lot of choices for this possible KTT. Like it's n choose this number is big. And therefore, the probability of something going wrong for any single choice of t has to be very, very small. We're trying to beat a union bound over that many choices, an exponential number of choices. And also, it can be sort of scary because if you imagine we have this many edges. Okay, so I'll be all right on time, I think. We have this many edges. I don't want to remove that eraser.
Go ahead and move it, erase it. Erase everything.
So I'm not really writing anything that important. Each vertex has degree about n to the 1/3 log to the 1/3, which is actually much smaller than t is, right? So there are bad t, or like t's for which we really have to worry. For example, t might be the entire neighborhood, or it might contain the entire neighborhood of a particular vertex, which seems unlikely, but there certainly exists such a t. Just choose your favorite vertex, look at its neighborhood, and make t contain it, because its neighborhood only has size this, and t has size that. So in fact, you could fit many entire neighborhoods into t, and that's dangerous because we're trying to show that we're going to end up with a blue edge going from here to here. So it's going to be bad if a lot of those edges turn red, because we want to argue that these edges from here to here are just sort of hanging out, waiting to get picked. If they stay open for a long time, then eventually we're going to argue that the probability is high enough that an edge has landed in there. But if we have a massive closure happening in there, then that's much less likely. And this picture is now scary because what happens, well, what if I choose an edge like this? Well, that turns all of that red, right? The entire, once again, it's the entire neighborhood of this vertex and the entire neighborhood of that vertex just turns into a big red thing. And that's bad for us. And also there's, maybe I won't, there are other ways that you can have massive amounts of red pop up all at once. So it takes an argument essentially that basically for any sets t on top and t on bottom, you really might have vertices like this, like a vertex where all of its neighborhood, or maybe just a significant part of its neighborhood, is contained in here. But you don't have that many. You don't have that many vertices that are like that. So this event can happen, but it's less likely. So that's really the work that we had to do beyond, that was not given to us for free thanks to this general theorem that we had proven before. All right. So what is there for the future? So Deepak and I might do this. We're almost done writing the K2 two-part, and we're not sure whether we think it's worth writing up the other part, but of course you could replace 2 with whatever fixed, you could replace 2 with 3 or more. You could also generalize to a longer cycle, because a K2, you can think of that as a complete bipartite graph, but it's also just C4, right? So you could generalize by choosing a bigger complete bipartite graph or just a longer even cycle. And then you could attack the bipartite Ramsey for a cycle versus a KTT. But the more, I mean, that morally should just be a matter of running through the same stuff with the same methods and maybe more work and more of a mess. But maybe the bigger open question where the method really isn't clear is getting, I mean, all we did was shave off a square root of log off of the best known lower bound. And so how much clicking will this require? The lower bounds that we were working on, here we go, the power of t is off. The power of t here is this, and the power of t there is that. So when s is 2, if you ignore the logs, we're in between t to the 3/2 and t squared, and shaving off logs really isn't putting a dent in any of that. So what we'd really like to do is improve either of these powers of t. And as far as I know, there isn't a strong reason to believe that either one of these in particular is the correct bound. So yeah, we'd really like to make any progress along those lines.
So what do these extremal graphs look like?
What do you mean? Which extremal graphs?
So the K2T free colorings.
The K, like, I don't know where I'm clicking to, but it's more specifically, like, are you asking
No, I
about a
mean,
specific
like,
value of?
No. So you're looking for the smallest n where the KST exists, right?
Yeah.
So if I do n-1 and I do the coloring where you don't have the KST, are these blow-ups or like, are there any properties that these graphs have?
I don't know. I think probably not enough is known about this because, I mean, even in order to know what n-1 is, you'd have to know what the Ramsey number is, right? Yeah. This is not known except in small cases.
I see.
So yeah, I couldn't tell you whether it's a blow up of something or what.
Up to t equals 5.
It is
So,
up to t equals 5. You mean these are the ones that are known?
B25
B25
is the highest.
So like for this one, is it unique for 2-2?
So I can draw it. It's just basically the blue graph and the red graph are both just going to be an 8 cycle. And I guess it's, yeah, the rest of them are red. And if you stare at it, you'll realize that the red graph is also an 8 cycle.
I don't think that's the unique one though.
It's not unique?
No, I think there's like, in one color you take two vertices which are dominant, opposite each other that are not adjacent. So like you have vertex 1 on both halves. And the leftmost vertex is adjacent to everything on the side.
Right. Like this?
And then the other, yeah. And then you can add in an edge between the two of them.
Like this?
Yeah, and then the complement has no...
Complement is K3.
Right, the complement
is something like this. There's, maybe you add in like matches between those or something. I don't know.
If you delete the leftmost edge, you put in a perfect matching in the rest, I think that would work. I don't know if that's what the right graph would be.
Yeah, so that doesn't have a K2 and neither does its complement. I think.
Okay. I suppose, so this is a blow up, isn't it? Wait, it's hard to look at this and tell whether it's a blow up. For me it is anyway. So yeah, I don't know, I think you asked a very hard question.
Okay.
Thank Patrick.
Thank you.
I hope it was it.
I'm sorry?
Yeah, I hope this was it.
Yeah, I got to my questions for the future, so that's basically, that's it, right?